All right, welcome. First of all, thank you for staying this late. I'm sure many of you have planes to catch, and many of you haven't woken up from last night. I know it was difficult getting out of bed this morning. So my name is Deepak Singh. I own the product management team at AWS that's responsible for instances and instance performance. I also have with me today Christos-Kalantzis from Netflix and Steve Jones from AWS, who will talk about some specific examples of how you can use specific EC2 instances that, to help you increase the performance of your applications. So welcome. I'm from Seattle, so I have to put a cup of coffee up there. I haven't had enough today. After this talk, that's the first thing I'm going to do. I'm going to talk about three things. The first thing I'm going to talk about is instance types. Surprise, it's a talk about instances. The second thing that we'll talk about today is performance. And the third thing that I'll talk about is introduce a new concept for EC2 called generations. For those who have been on EC2 for a long time, I think this will be an interesting sort of change in how we think about new instances and how we plan to approach them going forward. So EC2 has many instance types. I've been told by folks our instance list looks like a Burger King menu. It's not necessarily an incorrect description. You can select your instance type. You can choose how many you want. You can choose the availability zone and region, and you can launch them. That's a simple thing. Most people will launch one or two. If you're Netflix, you're launching thousands, and they're not using the management console. They've probably got other ways of doing that. But the way we think about it is instances are building blocks. You can think of them as Lego bricks that you can use to build any application that you want. We have a number of AWS services that take advantage of these building blocks. You heard about AppStream and Workspaces or other AWS services like Elastic MapReduce. Their goal is to take these building blocks and package them in ways that make it easier for you to use for your applications. Or you can build your own applications and also own services on top of these building blocks. So we treat them as fundamental primitives, especially with the APIs that come with these that will help you build your applications better. We divide them into these categories, and I'll go a little bit into how we think about these categories in a second. General purpose, which are M1 and M3 instance families, compute optimized, memory optimized, storage optimized, GPU, and micro. But the key takeaway from this is, in the past, we used to just give you a list of instances. We used to say this is high memory, this is high CPU, and we were mostly referring to the ratio of compute and memory when we talked about these. But over the years, we've definitely learned from our customers, and we have enough scale and enough variety that we've actually started optimizing our instances for specific workloads that we think they're useful for. So we have a number of workload optimized instances. An example of one is something that we launched just a couple of weeks ago, and you've heard being talked about at reInvent. Probably most in context of AppStream, which is the new service we launched, which takes advantage of these new instances. G2 is a GPU-based instance. EC2 already had one, the CG1, but the CG1 was not capable of doing graphics. The GPU part of that was for general purpose computing. You had to use something like NVIDIA's CUDA programming model and use it for parallel programming and other scientific computing topics. The G2 instance, on the other hand, is based on NVIDIA's GRID technology. It is explicitly designed for remote streaming and graphics applications. If you were at John Phillips' session this morning, you got some good examples of how companies like Autodesk and Schrodinger, or if you've been to the AppStream booth downstairs, how AppStream is using the G2 card to essentially do frame captures and ship them across the wire using proprietary protocols, the NVIDIA GRID SDK, and other features that come along with this instance. It's designed for folks who want to do remote visualization, remote graphics. It happens to be usable for general purpose computing as well. So that's the G2 instance. I won't talk too much about it because there have been other sessions on this one before at this conference. The other instance family that we talk about a lot and is probably used by a large number of people is the compute optimized family. And specifically, the instance type that we launched a couple of years ago was the CC2 instance. And just to set the context of generations, over the last 2 or 3 years, we've launched a number of high-end instances, something like a CC2. It's a very large instance. It's designed for performance, and it's very useful for that. So for specifically the CC2 instance, comes with a 2.6 gigahertz Intel Xeon E5-2670 processor. So that's a Sandy Bridge class processor. It has 16 cores, 32 virtual cores, which is how we spec it. It has a 10 gigabit cluster networking framework. So cluster networking is a feature of EC2 that allows you to logically launch instances into this construct called a placement group, and every instance within that placement group gets a full bisection bandwidth at 10 gigabits per second. So it had all these properties, and that allows us to do things like run HPL on it. For those of you who don't know what HPL is, it's used for the top 500 supercomputing competition. I don't think they like calling it a competition, but regardless. It's a good stress test for us because it allows us to test the stability of our clusters, of our fleet, about looking at our network efficiency. And so like everybody else, when we just before we launched CC2, we ran HPL on it. We ran a 17,000-ish core cluster, got a performance of 240 teraflops. The theoretical peak was 354, so you can see we're leaving quite a bit of performance on the table. This cluster had an efficiency of about 65 to 66%. But it's pretty good for a large Ethernet-based cluster. And it was pretty unique at the time because it was the first time that a virtualized, pure virtualized system had been in the top 50 supercomputers ever. It's no longer in the top 50 because every 6 months you pretty much plummet. So we are pretty happy with what we did and what we've learned from this instance over the years. It's very popular for all kinds of use cases, from batch processing to just running web servers to the HPC-style use cases that we designed it for. The other area where we focused a lot over the last year is I/O. You heard Werner talk a lot about I/O in his keynote, and it's been a focus of AWS now for about a year and a half. Last year, about this time, we launched 2 products that were focused on I/O. One was EBS provisioned IOPS, and the other one was the HI1 instance type. So HI1 instances are SSD-backed instances. They have very high random I/O performance. You get 2 terabytes of SSD, 2 logical volumes, 1 terabyte each. And to talk a little bit more about how HI1 instances can help you scale your applications, I'd like to invite Christos from Netflix, who will talk about how they use HI1 for Cassandra.
Good afternoon, everyone. My name is Christos-Kalantzis. I manage the cloud database engineering team at Netflix. What does that mean? We run Cassandra in the cloud. About a year ago, we were given a few High-1 4 extra large instances, and we started playing around with them. We wrote a tech blog on it, and we showed that they've got a lot of IOPS. But what does that really mean from an application? Well, today I'm going to talk about what we saw in the past year using High-1 4s. We saw higher application speed. We saw efficiency in operations and better data quality for application developers, and cost savings. So let's talk about those higher application speeds. So like I said, we wrote a tech blog. We showed the amount of IOPS the High-1s have, but didn't really show off if you compare an M2 and a High-1. So what I did a couple of weeks ago, I spun up a 6-node Cassandra cluster. I put 250 gigs of data per node in the cluster. And the reason for that is I wanted a data to memory ratio of about 3 or 4 so that you're not just reading all the data from the file system cache. I used a tool called Cassandra Stress. Cassandra Stress is easily available. You can download it. It's open source. And I also included the exact options I used when I ran Cassandra Stress on this cluster. So this is a little picture of the test. So I had 3 M2 4s running that Cassandra Stress tool, all in different zones. And I created a Cassandra cluster. For those who have read how we deploy Cassandra, the nodes are equally distributed across availability zones. And I ran the test twice, once on M2, and the only thing that changed was the instance type of the Cassandra cluster. So same configuration, same AMI. All I did is I ran it once with the cluster being on M2 4 and once running on High-1. So this is what it looks like when you run it on M2 4. So the throughput, and just to backtrack a little bit, so the clients were not throttled at all. They're throttled only by the response time of the Cassandra cluster giving the response to the request. So the throughput on the M2 4s for this particular test was around 500 read operations per second, with an average latency of about 100 milliseconds, a 95th and 99th percentile latency of 0.6 seconds and about 0.8 seconds, respectively. On high ones, the throughput was over 20,000 reads per second, with an average latency of 2.5 milliseconds, a 95th percentile of under 6 milliseconds, and a 99th percentile of under 8 milliseconds. So that's a 40 times increase in throughput. Same test. Better latencies, 37 times better at the average, and about 110 times better at the 95th and 99th. We also took a step back and looked at, okay, fine, applications will run quicker, but what does it mean from an operational point of view? For those who know Cassandra, Cassandra is a benefit now, pay later kind of distributed database. What does that mean? Writes are immutable to SS tables. So eventually, you need to compact these SS tables. And that, as you can imagine, is a very I/O-intensive operation. In the past, we used to do it one node at a time within the ring in serial. Well, with the high ones, we have all this available I/O, so now we can run these compactions in parallel, and they run much faster as well. So operational tasks, we just breeze through them now. Cassandra is an eventual consistent distributed database. What does that mean? You write to one node, and then it'll eventually replicate to other nodes. How many is how you configure your cluster. One thing a lot of application owners will do, especially more conservative application developers, is they'll send high consistency requests, both at the read and the write, because, hey, it's eventually consistent. I want good data. When I read once and twice and 3 times, I want the same value to be returned. Well, Cassandra has a tool called repair, and what repair does is it'll go through all the nodes, compare the data, and wherever there's holes, it'll fill those holes, and you get back to a baseline of consistency across the whole database. Well, although it's not as I/O intensive as a compaction, it still takes, it would still, our clusters running on M2s would still take a hit. So by running on high ones, that repair takes a lot less time, which means I can offer to my application developers a cluster that is a lot more consistent. And so now, when they make read requests or write requests, they're more comfortable using a lower consistency level, which increases their, reduces their latencies, increases their performance. Let's talk cost savings. So until the high ones came along, Netflix always used this model of one application per cluster, per Cassandra cluster. And so we couldn't really do multi-tenants. The reason for that is if one tenant misbehaves, well, both tenants suffer at that point. So because the high ones offer all this room at the top end, we can now have multiple tenants on the same cluster. These are the prices as of last week, the list prices as of last week for M24s and high ones. So as you can see, as soon as you get a second application on that cluster, you've got immediate savings. But there's so much room, there's so much ceiling, such a high ceiling, you have so much room that you can have 3, 4. I think I've got one cluster running 5 applications. So there's considerable savings there. When we used to size, and still when we size Cassandra clusters, when we were on M2s, what we used to do is we look at how much data is going to be stored in that cluster. And we try and get close to a data to memory ratio of 1 or below 1. Like that, as the cluster got warmed up, you'd be serving a lot of the data off of the file system cache. Well, with the high ones, you don't have to, you can have a ratio higher than 1. You can have a ratio of 3 or 4, like I showed earlier in my performance test. So you're using less nodes at this point. And since you've got all that room, you don't have to grow the cluster as often or as big, so there's more savings there. For anyone who works in operations, more machines you have, more chances of things going wrong. Well, because the high ones allow me to have smaller clusters, use less nodes, there's less firefighting. Less firefighting means I have a smaller operations team. This operations team, instead of putting out fires, they can now concentrate. They've got their head above water, and they can concentrate on automation, on building tools that will predict the fires and programmatically mitigate those problems before you get paged at 3 a.m. You pretty much achieve this kind of DevOps nirvana. And if you have all that time on your hand, then you can do stuff like this, where we've now unleashed Chaos Monkey on our Cassandra clusters. Now, let's talk about some caveats. When I first saw the specs for the high ones, this thing just popped out at me, 10 gigabit per second. But you get 10 gigabit per second only if you're in the same cluster placement group. If you're familiar with Netflix's cross-zone availability model, where we spread our applications across 3 zones, well, you don't get the 10 gigabit across zones, and you definitely don't get it across regions. So, there is a footnote, read the fine print, but, be careful about that. And the last part is, for those who are Linux sysadmins here who work on Iron and who've played with SSD drives, we talk a lot about the high ones being SSD backed. Well, they are SSD backed, but it's not the same as running a Linux server or a physical server with hardwired SSD on it. The virtualization obfuscates some of the SSD advantages. So for those who've worked with SSD drives on Linux boxes, all those sysconfig changes you can do to eke out even more performance, well, that's not really applicable in the high one instances. So it's not to say it's bad, but just frame yourself as this is an EC2 instance with a lot of IOPS. So that's what we've seen over the last year. I hope this information was useful and help you make the right decisions on your EC2 instance choices. Thank you.
Is, as we've developed new instance types, is choosing the right instance for the right application. As Christos showed, an M1 is $1.64 an hour. M2, sorry, and an HI1 is $3.10 an hour. Your default reaction might be, oh, $3.10 is too expensive. But when you start actually thinking about how you're designing your applications for those instances, you'll often find that you can save a lot of money. And that's kind of how we think about designing and developing new instances. We choose a metric that we care about for that particular workload optimized instance. And we try and make sure that for that particular metric, we're giving you the best instance possible. So for HI1s, for example, our goal is to be the cheapest dollar per IOP inside EC2. If IOPS is what you care about, you will not get a better cost per IOP here. If you care about dollar per compute performance, you want to be on a CC instance, because if you can fill it up, because you'll get the best best bang for your buck there. Similarly, I'm going to now talk about memory optimized instances. And the goal of memory optimized instances, quite simply, is to be the best dollar per gig of RAM that you can get inside EC2. So if you are completely memory bound and you can fill up the CR1 instance, which has 244 gigs of RAM, this is the cheapest platform you'll get. In fact, we have a lot of customers who will take a CR1 and basically fill it up with JVMs or something like that till they basically run out of memory. And it is the best, that's how they use it. It's not just for the kind of memory bound applications you might think about. Like the CC2, this also has a really fast CPU. In fact, they're the same exact CPU and the same cluster network. And the use case that we designed this for and we were very interested in was in-memory distributed analytics. Not only does the CR1 instance have a lot of memory, it also has very fast memory. Now I think everything has the same fast memory, but for example, the memory on CR1s is a little faster than the memories on M2s, for example, because it's a newer generation hardware. And we wanted to make it easy for people not to run just memory-bound HPC applications, which is where CC2 fell a little short. We really, really wanted to focus on in-memory analytics, which is becoming quite popular as the cost of memory has gone down. And the kind of applications that we were looking at are things like SAP HANA, which is an in-memory analytics system. And to talk a little bit more about how you can make how EC2 instances work for HANA, I'd like to invite Steve Jones, who works very closely with SAP from our partner team.
Thanks, Deepak. Appreciate that. Let's go the right way here. So as Werner mentioned in his keynote yesterday, I think it's no surprise that we're seeing more and more in-memory type applications. The latency differences between magnetic disk and memory are sometimes astronomical. So in some of the testing we've done with SAP HANA, we're seeing for database workloads that RAM is sometimes faster, up to an order of magnitude of 100,000 times. It really depends on the workload, but you're seeing more and more applications like SAP HANA take advantage of direct in-memory access. So let's talk a little bit about HANA and what it is. So how many are familiar with SAP or SAP HANA? So back when I started working with SAP systems in the late 90s, it was a classical ERP system with one single database. It was primarily Oracle at that time. And everything was stored in a row store, right? Just a typical OLTP type database. But they would also perform massive queries on this same data, right? So the data would continue to grow and grow, and they would be running OLAP type reports in the same system. And so to get around this, SAP created a new system type called the business warehouse, and you started seeing enterprise data warehouses born at that time as well. And so still, they had issues of nightly loads. The data was not always up to date. And so they came up with this idea of what was called an in-memory appliance, or BWA. At this point in time, the BWA appliance, while it was in memory, it was just indexing in memory. But again, data continues to grow, and as we hear a lot, we talk about big data problems or big data opportunities today. So over the last, I would say, 3 years or so, they've come up with this new platform. It's based on some technology, pre-existing technology that they had in place, and a lot of new development effort. But it's called SAP HANA, and the idea is that in a single system, a single database, they've got both a row store and a column store. It's highly compressed. So we've seen compression ratios of 5x to 20x. And with that compression, obviously, that requires a lot of CPU compute capacity. The other interesting thing is that the data can be highly partitioned and distributed amongst multiple nodes. It's a very scalable system. And so when we started talking to SAP about scaling, we get scaling really well. And so they were actually pretty excited to work with us on testing, and I'll share a little bit about that in a minute. The other interesting thing is typically up until about a year ago, customers could really only get HANA, the SAP HANA product on a hardware platform, on a bare metal appliance that was shipped by rack into the customer's data center. And sometimes it would take up to 4 to 5 months to actually get this, depending on demand. So we were actually excited about the opportunity, not only because of the compute characteristics and the performance characteristics of the instance types that Deepak has mentioned, but also just the agility that provided customers to be able to actually do workloads like this in conjunction with some other workloads they were doing on the cloud as well. So about a year ago, we worked with SAP to vet out the CC2 platform, which Deepak mentioned. But just recently, within the last 2 or 3 weeks or so, we actually announced support for the CR1 8 extra large instance type, which, as he mentioned, has 244 gig of RAM. And it's very interesting because up until, again, about 2 weeks ago, the only option for running very high memory workloads would be to get an on-premise appliance. And so these appliances were based on a Westmere type CPU. And typically those come with 2 CPU, 10 cores, and about 40 virtual CPUs, or 40 CPUs with hyperthreading. And when we did performance testing, bare metal versus our CR1 8 extra large, we're actually very surprised and very pleased. Our team has done a lot of tuning to make that in-memory experience really applicable even on a virtualized platform. And we actually saw very comparable query performance, and in some cases we actually saw even faster performance for queries. It's difficult to give you discrete numbers, as it wasn't an apples-to-apples comparison. As I mentioned, the on-premise appliances typically come with Westmere CPUs, and we're using Sandy Bridge. So these processes are a little bit faster, but we do have less threads. So again, quite pleased. The other thing that we're making use of, which HANA uses quite heavily, is NUMA, the NUMA topology. So we're quite pleased that there was you were able to expose that to this workload. Another thing we hear from customers is HANA is very expensive. The hardware is expensive, the licensing is expensive, and what we're really pleased to be offering our customers is the ability to deploy this in a very price-performant way. Let me give you an example. So I was talking to a customer yesterday, actually out of Japan, and they were exclaiming that they bought a couple $1 million hardware appliance back last January, and then the tsunami hit. And so they were impacted by hardware availability, right? And so then they went to a supplier in Germany. It ended up taking them 4.5 months to actually get their hardware. You think of all that time, right? They had already made the business case for purchasing this, and all that time that they had to wait to actually start development. Now today, with the latest offering on the CR1 platform, you can actually spin up a 5-node CR1 HANA cluster in about 20 minutes. Fully automated and fully operational. So we're pretty excited about that. And the price is awesome, actually. So we're very pleased with that, and our customers are too. So let me make you aware of an academic exercise we've been doing with SAP around scalability. So they came to us with a request about, what was it, about 3 weeks ago, Deepak? For about 10,000 cores. And so we're working on building out a 10,000 core HANA cluster on AWS together. And here's some preliminary results. We've actually gotten up to 1,776. It's a nice American number, right? But some of the characteristics of this is some of the performance, early performance numbers. We're actually seeing about 3 million queries per hour. This is 111 CR1 instance type, CC2 instance type. 800 million rows per second, a total of 60 billion rows, and we're actually, continuing to work on this. We're actually really excited about this opportunity. So if you want to get started on HANA and try it for yourself, there's actually a number of ways to go about this. So there's a free HANA Developer Edition if you just want to see what in-memory is all about. You can actually get it on the SAP Developer Center. Another one that's really interesting, we're seeing customers use a lot, is the one that's available on our marketplace. It's called HANA One, and the really cool thing about this is it's 99 cents per hour for the SAP license, which, if you know HANA, is typically pretty expensive from a licensing perspective. It leverages the CC2 instance types, so you get all those great performance characteristics that Deepak was talking about. And we're seeing customers do some really interesting things with this. Like, so they'll combine elastic MapReduce to process very, very large data sets, and they'll take the resulting output and stuff that into HANA, and then start doing some of the in-memory analytics on that, turn that over to their business people for analysis. We've also seen some people in a similar vein take that and use the spot market to leverage even lower cost options for the CC2 and other compute instance types. And then recently the announcement I talked about around the CR1 instance type and being able to scale very large HANA clusters is available on the SAP HANA Marketplace. And again, the provisioning time takes about 20 minutes, which is just night and day from what it used to be. So we're very excited about that.
Thanks, Steve. So you heard a little bit about workload optimization and how we've spent over the last couple of years. We've spent a lot of effort trying to develop instance types that are specifically targeted towards compute bound up, giving you the best possible compute we can on EC2, on I/O, on giving you a lot of IOPS at a really good price, on giving you memory performance at a really good price for applications such as HANA. So where do we go from here? I think the biggest change that you'll see in EC2 going forward is the concept of generations. So how many of you have been using EC2 for over 3 years? Excellent. And you've all used M1 instances over those 3 years. And you've probably spent some time trying to figure out what hardware type you land on. Because especially if you are particularly concerned about certain aspects of performance, you will run into the natural challenges of different hardware generations. We spend a lot of effort trying to make hardware performance consistent across hardware types, but there are certain things that are difficult. The fact remains that our friends at Intel keep increasing memory bandwidth as you go across generations. It's difficult to control. So what we decided and what we've started doing is we're not going to do that anymore. If we are getting significant performance improvements from a particular generation of hardware, whether it's processor improvement, whether it's memory performance, whether it's disk performance, we would prefer to release it as a new generation. There are certain rules that we have, and they're still evolving, but you'll start seeing us do that, and you've already seen announcements made at reInvent, which I'll talk about a little bit more, that speak to that direction. The other thing you'll see us doing is CC2, HI1, everything. Well, one big instance at the top of the food chain. Not everybody can fit their data into 240 gigs of RAM. Not everybody has 2 terabytes of data and needs 300,000 IOPS or has 5 applications that they can put on a single Cassandra cluster. So we heard a lot from customers like, hey, can you give us some of these benefits, but at smaller sizes? And as part of this effort to move towards new generations, effectively what we are doing, and I'll use C3, which I'm going to talk about as an example, and I think that will illustrate what we're trying to achieve. So in general, if we are getting latest generation hardware, the chances are we will launch that as a new hardware instance generation. We also want to, because we can do that, we can also expose specific hardware features to you, such as Intel's AVX floating point extensions, which give you double the floating point operations per cycle, which is essential for great floating point performance. There's features such as AES-NI, et cetera, that we can expose to you for encryption. So we want to do that. SSDs are evolving probably faster than anything else right now. Every generation of SSDs is significantly better, and we want to take advantage of that. And in general, we like SSDs. And this feature is something that I'll talk about in a bit. This is stuff that we've done. You probably heard and are wondering what enhanced networking is, and I'll talk a little bit more about that. And we want to be able to give you that as well. And in the end, the goal is, hey, we want to give you better price performance, even if the absolute price is a little bit more, but from a metric that we care about, we want to be better. So the first instance type, you heard Werner talk about this, is the C3. We think about it as our 3rd generation compute optimized instance with C1s and CC2 sort of being first and second. The C3 has the best raw compute capacity you can get on EC2 today. It is based on a 2.8 gigahertz Ivy Bridge, so the E5-2680 V2 processor, which Intel announced in September. Earlier just a couple of months ago. It supports turbo, so if you are, depending on your workload types, you can get over 3.4, 3.5 gigahertz of CPU speed that it'll go to. So it's a really, really, really fast processor. We have taken the concept of clustering, which was available on just this one big instance, like the CC2 or the HI1s, and made it a feature. It's available in every single size that we give you. The bandwidth that you get out of it is dependent on the size, but essentially you're going to get that low jitter, low latency network performance, even on smaller instances. You don't have to get a CC2 or a scale instance to be able to get clustering as a feature. And here's what the specifications look like. You go from 2 virtual cores to 32 virtual cores, where a virtual core is a hyperthread. Your memory, compared to C1, you have double the memory per virtual core. So you go from 3.5-ish, almost 4 gigs of RAM, all the way to 60, which is very similar to what CC2 was. And instead of hard drives, you have SSDs on everything. These are not focused on IOPS. We don't do some of the tuning and steps that we do on the I/O platforms here, but we're giving you SSDs, with the biggest one giving you about 640 gigs of SSDs across two volumes. And the price goes from about 15 cents an hour for the C3 large to $2.40 an hour for the C3 8 extra large. Let's focus on the C3 2 extra large. That's roughly the equivalent of a C1 extra large if you are used to using C1s. It has 8 virtual cores, double the memory of that one, that is 7 gigs of RAM. It has 2 small SSDs, but the price of a C1 extra large is 58 cents an hour. This one's 60 cents an hour. But the performance is that much better. Depending on your workload, it'll be some between 15% to maybe even double the performance especially for floating point ops, that you're going to get. So there is no such thing as a specialized cluster compute instance. That's your C38 extra large. We support clustering across the board. And this is the kind of change you will hear from us as we go towards this new generations model. Like everything else, we ran high performance Linpack. We actually just ran it. It'll show up next week as a supercomputing conference. So when the top 500 gets published, that's what we got. 26,496 core cluster, 484 teraflops of performance. Peak performance was 593.87. I'll come back. So if your mental math is good, your CC2 cluster was 65% efficiency. This one is over 80% efficiency for a cluster that's significantly larger than that one. So we were pretty pleased, especially in Ethernet. That's very hard to do. And this is an example of the 3 clusters we've submitted over time to the top 500 and how our performance has improved. Now, we are not trying to do this as I could always build a bigger cluster and get a higher rank. This is our stress test for seeing if we can actually launch this thing. So we do it as that, and whatever cluster we build, we submit it, and we're usually pretty happy with where we end up. I don't know what our rank will be. Most of the top clusters in the world now are funded by some government. They have all kinds of accelerators in them. They're not using pure CPUs. In June, we would have been number 55, 56. We'll probably be lower this time, but the performance is pretty awesome. What I really like actually is this cluster. This is a 512 node cluster. It's not that big. You still get 164-ish teraflops of performance at over 90% cluster efficiency. And this would have been in the top 250 last time. And this is 500 nodes. You can sign up today, ask for an instance limit increase, and get it if you dare to run a job that large. So that's C3. It's our next generation compute platform. If you're using C1 extra larges today and you like the performance that you get out of that, or CC2s, I would strongly encourage that you take a look at C3. You should be super happy. If you're network bound at all, you'll be really, really happy, and I'll get back to that. The other instance that Werner announced is the I2. So Christos talked a lot about how HI1 has been very good for Netflix and giving them great Cassandra performance. What if we can do better? So the I2 is not available yet, but it'll be coming soon. This will be the best price for IOPS that you can get on EC2. It'll be substantially better than the HI1. It has more sizes than the HI1, which is a single size. It has more SSD. It has more IOPS, and it has more memory. It's got everything more because more is good, right? So these are the specifications. So the I2 4 extra large is effectively the equivalent of the HI1 4 extra large. You have 16 virtual cores. The HI1 had 60 gigs of RAM. This is double the RAM. The HI1 had 2 terabytes of SSD across 2 volumes. This has 4 devices, each of 720 gigabytes. And the largest one is essentially 5.5 terabytes of SSD storage. And if you look at the price of the 4 extra large, it's just a little bit more than the HI1 today. Even though it has got double the memory, a much faster CPU, much more disk. So that's the kind of thing that we are trying to take advantage of. And again, you have 5 sizes. Every one of them supports clustering. So you can do some pretty good stuff with the I2 instance. So what kind of performance do you really get out of it? That's how much. On the on the I2 8 extra large, you can get over 350,000 random 4K random read IOPS. And here's the fun part, is the write IOPS, because the previous generation of SSDs tend to write really well. We've measured over 320,000 random write IOPS, if you care about write performance. And the 4 extra large is effectively proportionally half of that, and so will all the others will be. So we're pretty excited about the kind of performance we can drive out of this thing. You have less than 100 microseconds of request of I/O latencies. It's quite a beast of an instance. So that's the 4 extra large random I/O performance. The last thing I wanted to spend time talking about today was enhanced networking. It's a fairly fuzzy word, but it means something specific. Both the C3 and I2 instances and EC2 instances that we launch in the future will support enhanced networking. What does it mean? So we have a new networking stack. There's a caveat to this stack. You have to be running in a VPC, and you have to be using an HVM army. You only get this performance if you're doing those 2 things. There's a specific network driver that you have to install, specifically an SRIOV driver. So we're using a device virtualization feature called SRIOV to deliver this kind of performance. You get very low latencies, you get low jitter, network jitter, and very, very high packet per second performance. I'll give you a wonderful unitless graph to show how the PPS increases. That's CC2 8 extra large on the left, C3 8 extra large, just a normal C3 8 extra large in the middle. They're roughly the same PPS performance. If you use an enhanced ARMY with the right driver, it's over 5x improvement in PPS performance. We essentially our goal is to give you, people often ask us, hey, can we have bare metal in the cloud, et cetera. Our goal is to essentially give you the same performance characteristics, whether it's SSD performance. So one of the lessons we learned from the HI1 experience was, hey, we were leaving some SSD performance on the table, which is why we're giving you specific devices, which allows us to actually give you the specific devices, and we're not really leaving much on the table anymore, if at all. Again, similarly with packet performance, we used to, obviously it's not just the SRIOE part, but it's also the network stack that we've developed, which is why it has to run in VPC, because you get those capabilities there. Here I am going to show you units in the next graph. These are ping latencies in an availability zone. You're running in a common cluster placement group, but the placement group can be really large. The lines going from top to bottom are the 50th percentile, 90th percentile, the 99.9th percentile, and the 100th percentile. The 100th percentile is the very worst latency you can get. These are points that have been collected over a very long period of time. There's hundreds of data points in there. This is the part that you get with this enhanced networking. If you look at the average, it's pretty much a flat line. You're getting no network jitter. But the fun part is that green line over there, which is your 99.9th percentile network latency performance. It is essentially flat as well. Your latencies are rock solid across a period of time. And for those people who say, oh, networking in the cloud is highly variable, if you're using enhanced networking, it won't be. Even at the 100th percentile, which is the very, very worst. So by the way, your y-axis is microseconds. So the worst performance you'll get in general is about 140 microseconds. We have one outlier. We'll have to go check what it was doing. But in general, you're going to get super great performance all the way down to essentially two instances just ping-ponging to each other at 80 microseconds. And this is, all you have to do is run with the right ARMY. There's no extra cost for this. You don't have to do anything special. So with this generations model, with some of the work that we've done over the last year, we have brought these features, and they're not just available at the largest sizes. They're available at pretty much all sizes. Not shown in graphs, but for smaller instances, what you'll notice is that even for smaller instances where you might think that, hey, there'll be more impact from more multi-tenant environments, you will not see this. You will not see variability in network performance. So this is where we started before reInvent in our workload optimized instance types. This is where we are now. The I2 is something that will be coming very shortly, and there'll be more to come next year. So with that, thank you very much, and we'll be happy to take questions.